Hey everybody, this is Matt, and today I'm going to be talking about signed distance fields, so implicit bodies and their representation inside nTopology. Reason I wanted to do this is because I still get a lot of questions about working with fields as opposed to bodies. Again, I'll shout out Blake Corder. He has some awesome videos on what he calls intermediate level and above techniques for these sorts of things, but I kind of want to show it in a simple manner while also showing some really cool things that you can do with your signed distance fields, and then what I call gradient control, which is understanding the rate of change from your visible surface in or out, or from body to body. The reason this is so important is because you can use the power of this to control things like ramps very finitely, as well as start to get people to understand that there's a whole world outside the visible. I'm a mechanical engineer, so I like the tangible, I like the visible. However, when you're dealing with things like fluid flow, thermodynamics, acoustics, vibrations, things like that, there's actually a huge amount of under the hood power that nTopology can provide outside of the scope of just creating an additive thing. Even though, of course, it is an additive software and it's good at that. So one of the best ways to visualize your field is to select your body and press F. I like to make my field relatively large enough, and then I set a contour interval. I'll show here at 1. Check probe values, and then you can take a look at where your values are in space from this field. So the way you can visualize this is pretend I'm dropping this shape inside of a puddle of water or a pool of water, and these are my ripples that go out from the field. If I hide this body right here, you can see negative in, positive out. If I do that with a cube, similarly, it's the same thing. Negative values on the inside, positive values on the outside. So this is the signed distance field representation. So even though I only have a body here in the middle that's visible, I have this whole world of things that are existing inside and outside the body that are usable. They're just not seen. Another way you can kind of look at this is by using a gyroid field. The gyroid field in and of itself is not a visible thing. If I tried to view it, it's not something that's going to be representative. So I can visualize it one of two ways. One of my favorite ways to visualize fields is to set a field bounding box. And what this is going to do is bound the field and show the field as a surface, kind of a non-dimensional, non-thickened surface. So I usually have a cube up here, a real big cube that I usually call BB for bounding box. And that allows me to just take this cube and grab the bounding box. So you can see here that here's my surface in space. I'll go ahead and turn the cell size up so you can kind of see it. So there's our nice gyroid structure. We can see that in space. Again, another way I can visualize this field even before I bound it is to take a look at this field bounding box. You can see here that my gyroid field is non-dimensional at this point, so it's going to go from a value of 1 to a value of -1, kind of cyclically. When working with fields versus working with something like the gyroid bodies, the gyroid bodies are already given dimensions. They've already been brought into real land, as I sometimes call it. The nice thing about working with fields is it's always -1 to 1. And that's really good because you don't have to add your units in until later on. However, the downside is that how you control your gradients matter a lot more. You can't just kind of fudge the numbers to make something look good, especially if you're dealing with things like fluid flow or thermodynamics, where the change in temperature over time, or the change in fluid flow, or mixing of those fluids is something that's actually really, really important. So let's go back to our sphere. Take a look at this again. So what I want to show you, I think is pretty cool visualization. So again, nTopology is implicit based, meaning we can perform math operations on implicit visual bodies. So I'm going to take this sphere and multiply it by 1. When I switch the field viewer to this, you can see nothing has changed. However, the sphere itself is still visible. If I show this result, it still is a sphere, right? They're the same thing. Now, if I close down the field viewer and I multiply this by 10, what happens? Now, on the surface level, I still have a sphere, right? You can see, maybe it's changing a little bit, although I just think that's the visual representation. But what I think is really cool is if you look at this field, one versus the other, this is what our gradient control is, right? We can see here that this is changing, so when I go out to this point, I'm about 20 away. However, when I view this field, you can see something here really cool. I'm way out here, and now I'm closer to 200. Now, why is that? By multiplying the sphere itself, we're actually controlling not the surface level equation, but we're controlling the gradient to and from the visible body. And the reason this is important is because when we talk about ramps, we're trying to go from a particular portion of an implicit body, we're trying to ramp to and from, we're trying to ramp from a point, from an axis. We can very discreetly control the gradient, how that goes and flows to and from the body itself. We can alter the gradient. You can do some of this stuff at the ramp level, but a lot of the times I like to control it at the gradient level because then I'm very distinctly aware of what's happening to my implicit bodies. And that gives me, again, a lot more power and control, over my entire design. So what's, one thing that we also can do that just is interesting, here's a couple of different things, is if I go by -1, I flip the values, right? So I can control my gradient that way. I'll just show you kind of a cool trick. One of the things I like to do sometimes is add in kind of some Boolean logic. It's probably not the right term. I'll flip sign. And then we'll throw a ramp in here, and we're going to make this ramp scalar values instead of fields. And we're going to grab our Boolean variable, we're going to tell it text, and we're going to say length. So what this outputs is a true or false. You see here it's at false, which is 5 letters. When it's true, it's 4 letters. So we're going to go from 4 to 5. We're using the text length. We're going from -1 to 1. So you can see here that right now this is outputting a 1. Now it's going to output a -1. And so I can actually grab this, throw this in here, and use this Boolean logic to flip. You can use this a myriad of ways. Trick to adding in kind of contextual choice-based things into your workflows. So if I wanted to have an option to add noise or have no noise, then I'm going to use this. The output's going to be a 0 or 1. I'm going to multiply that by the noise, and it's going to give me noise or not noise. I think that's a really cool trick. So now that we have this kind of cool values, I like to flip it negative because I think the gradient going from dark blue to purple is cooler looking than the teal to dark teal. So I like to visualize it a little better. So what we're going to do now is we're going to go do another step of multiplication. And we're going to multiply this by a ramp. And what we're going to see now is the ability to control your gradient as a function of distance. So we're going to go from x from -30 to 30, 0.5 to 2.5. And when I switch to that field, you can see here that, again, something really cool. Now we start to get something that looks more like what you consider in heat transfer, fluid flow, magnetism, things like that. The representative equations of gradients are so powerful in all sorts of things that are outside the scope, again, of the physical. So you see here that we're compressing these waves in the positive x direction, and then as we go into this negative x direction, the waves are going greater and greater. Because of the way the sign distance field works, you see here that as these guys kind of come around, it's not always going to close out the shape. And that's just because as these fields come together, how you manipulate them, if I turn -30, if I turn that closer to -10, you can see here that that's going to happen a lot faster. And at this -10 distance here, we kind of have a change. Another kind of cool thing that we can do is, again, use any equation you want in here. So I'm going to go x squared. I'm going to go from 0 to 30. It's going to yell at me for units, so I have to put in the proper units. And there you go. So here you can see that our gradient control is now a little bit different. So now I have this sort of peak in the center, starting at 0, kind of centered on this medial plane, and as I go out. So one of the other things I wanted to show is, you notice here that the transition points between kind of what I'm wanting, especially once we start getting in, to this asymptotic relationship, is not as smooth as I'd like it. So that's where our smooth field comes in as well. Smooth field helps sort of, I don't want to say fudge, because you can do it in a very controlled manner, but it helps to remove some of these almost anomalies in our gradients. And this is another thing that's really cool to see, is that at the field level, we're controlling how the field works, and we're manipulating the field even before it becomes a visible entity. So our smooth field, we're going to go ahead and grab our field here, and then it's going to yell at me again. It's going to say, hey, you need to have it bounded. So we'll go ahead and take our bounding box here. We'll drag our field in first, and then into the smooth field. Turn that down. And then I'll go ahead and switch over to the visualization of that. And here you can see, awesome. We've taken our field and we've smoothed out the kind of sharp intersection points. I really like to be able to use this, especially when I talk about, when things are changing, how I take the gradients, which I'll show a little bit later. Whenever you're working with vector fields as well, a lot of times the smoothing helps a lot, and because vector fields can be jerky, right? They're a derivative, so they're not always the smoothest. So I think that's kind of an important distinction to note as well, as we've got this really beautiful field now. Again, we can go ahead and flip it, flip our sign to turn the positive values. Another thing you can do with your gradients and fields, which is important when working with TPMS, is to be able to use the ABS function, and ABS just turns everything positive. So even though we have this 0 point still, kind of where we're at our surface level equation, we're going positive in and positive out. So ABS, when you're working with gyroids, allows you to bias the gyroids in to create more of a skeletal based gyroid, instead of like the sheep TPMS, and it gives you an incredible amount of power prior to bringing your field, giving your field units. And that's something that, again, Blake has a couple of really cool videos on how you bias those gyroids. Go ahead and delete that. All right, so we've got our fields. This is kind of showing you what what are some of the things that we can do with them. I wanted to show something else. Oh, it's working with even these implicit lattices as well. So cube, make it 20. Turn on my field viewer. Oops. There you go. So again, implicit lattice based on, our volume lattice. Give it a thickness, not 5.5. And then I can do the same thing. I look at my field, kind of where each of these lattice points hits in space. Look at the distance from each. And I can do the same thing here. I can control the gradient to and from where my lattice is. So that's really cool. Again, I see some of these sharp points. I could use the same thing, a smoothen field. So the direct physical result of the smoothing of the field is I'm going to take my lattice itself, and I'm going to smooth out some of these nodal interactions. But again, since implicits are fields, and since we're manipulating them at the fields, I always encourage people to go in and look at the field viewer in particular. This just gives you a good idea of what's happening with the part in its signed distance field as it goes throughout space. Here's something that I feel is an important thing as well, and that's when you start to use the remap function Sometimes things can get to the point where you get some unintended results, and I'll show you that here. And if you're not exactly sure how the remap function works, hopefully this will provide a good example. There's probably a lot more tools or videos, workshops that nTopology could show you on this, but I'm going to take an implicit variable. You can actually take, so if I take this volume lattice and I make it a variable, you can actually change it to an implicit body. The kind of the issue that I have, not the issue, but one of the things I don't like is if you turn that into an implicit body, it's not visible anymore. So I always make my lattice a variable here. And then what I'll do is I'll take this implicit body and I'll drag this in here. So now I have an implicit volume lattice, but I can still see what's happening if I want to manipulate the lattice at this level. So I'll have here's my volume lattice, here's it implicit, and what I can take with this implicit lattice is I can use it as a scalar field, and I can remap it. You can either just take the body itself, or you can tell it, hey, I want to specify the field. They're basically one and the same. Somebody that works under the hood may tell you if there's a huge difference in selecting one versus the other. I usually like to make it a field because I'm anal and because I'm remapping a field, not the implicit body, but that's just me. So what we're going to do is in Y and Z, we're going to just tell it, remap your Y values to Y and your Z values to Z, which means don't change them essentially. But then for X, we're going to multiply it by a ramp. Again, we're going to multiply X by something. So X in a span over X. So for my scalar field, I'm ramping from something to another thing. Sometimes I like to show what I'm ramping from too by using line segment. So my line segment, you can see here that I can do minus 25 and 25, 0, 0. Sometimes I'll color this something different just so you can see. So this will show the start and end of my points. I can also look at a field and create a field that's a distance field that just shows me where my values are in space. But this is a nice little trick that says, shows you where you're starting, from minus 25 to 25. So that way I know when I'm doing my ramp and I'm controlling my ramp, I know that if I'm going from minus 25, this is about where I'm going to start, changing an X to 25 over here. And then I'm going to go from 0.25, a quarter of X, to 4. Oops, I did that wrong. Scalar field, I want X. That's my fault. Minus 25 to 25. And then my out values are for 25 to 4. Or 4. I want 4, not 5. It's going to yell at me here. It's going to say you don't have compatible units. And that's just because, for some reason, it didn't do what I wanted to do. You see here that these values are not dimensions because X is already a dimensioned value. So even before we get into and try to show what's happening, I'm going to just take this field in particular and visualize it. So, alright, cool. You can see some cool stuff happening. So you'll notice here that this is where my lattice is in space. At the, let's show our line segment again. At the negative 25 value, I've started to compress. So if I change that to 0.5, let's say, I don't compress it as much. Let's actually leave that as 1. So you notice here that as we start to get into, I'll turn this to 2, some of these values right here, we start to compress. Here in our lattice region, you can see here, this is where the start of each of our beams are. And as we get a little bit bigger, let's actually turn that back to 0.25. As we get a little bit bigger, you'll notice here that we get some pretty crazy stretching. And you'll see what that does once we start to take our lattice and we want to be able to thicken it. So I have this remap field. What I'm trying to do is change the cellular spacing. So now I'm going to offset my body. You can offset or thicken. When you're dealing with kind of these beams or struts, these zero dimension struts in space, offset works and thicken work fairly similarly. If you're dealing with surfaces, then offset will offset from a surface positive or negative. Thicken will offset the surface from the median in both directions, and each direction is half of the thickness that you choose. That's an important kind of aside note. So I'm gonna offset it by 0.25. All right, interesting. So you see here that I have the compressed values over here. I have something wacky happening kind of as I start to approach my 25, and then I have what I kind of wanted, which was a larger scale over here. What happens if I go from -50 to 50? Okay, so you'll see here that that I'm getting kind of what I want here, right? I have a compressed value here and a bigger value here, but I still am taking essentially the available kind of tiling that I have in X, and that's getting compressed, so it's not as usable. So there's a lot of tricky math that has to happen if you're trying to take this volumetric lattice and compress it, because it's only going to use what it has from a remap standpoint. Again, this is the important thing about knowing where your field is, visualizing your field, because you can get a lot of unintended results if you play with things that and you're not exactly sure what's going on. So a lot of the times, if I'm looking at this volumetric lattice, I'm going to take this cube and I'm going to make it kind of my bounding cube. The reason I'm going to do that is because I'm giving myself a nice big area to work with. Now, this is obviously going to slow things down. From a processing standpoint, there's going to be a lot more stuff to process, but it's going to give me kind of more room to work with as well. Most people that are watching this probably already know, but nTopology uses kind of a dynamic renderer. So for things that are smaller, it's going to render them at the lower resolutions nicely. But once you get this kind of a lot of data, and you really got to turn it up to highest in order to be able to visualize what's happening. So at this point, I honestly don't care. I have a big cube, and the offset value is not, I don't want to use that whole space. So I'm actually going to intersect this offset body with a smaller cube, right? It's what I wanted as far as like my available space here. So that I'm starting to get. Let's go to 20. I'm starting to get something that I wanted, right? Which was changing the cell value, cellular grading, as a function of a distance of x. At a later date, I probably could show this, or if anybody's interested, you can send me a message here on LinkedIn where I'll be posting it, or on Slack if you're in the nTop education group. But how you set your bounds is important as well, because remember, when we're looking at our field in particular, you can see that we kind of get some weird stretching that happens here before we get into where we originally set our value of a quarter of x and 4 times x. So what happens here is kind of a function of I think it's a mix of the way nTopology handles the remapping, as well as the fact that you're using kind of this tiled method of non-dimensional struts. Now, I probably could verify this by actually talking with somebody before I go ahead and shoot off my mouth, but maybe have a conversation with Blake about the engine in particular. But what I find is it's very interesting is just how kind of there's like this asymptote here, right, where something strange and funny happens. So if you're trying to go from a particular cell size to another, you almost have to bias out your distance that you're trying to change over well outside your intersected value, and how you kind of control the math there is important so that you get exactly what you want. And I don't really necessarily want to go into the details, but we can maybe address that at a later date. Another thing you'll notice is even though I've offset by a constant value, you can see here in the x direction that there's a difference in my beam size from one to the other. And again, this you see that happening in our field. We are stretching the thickness of our field. Let's go with 50. No, it doesn't like that. So here we go. So we're stretching the thickness of our field, and you can see that happening in the gradient, whereas I'm saying 0.5 is my gradient, but here, the difference between, here in the center, until I get to the outside values, is smaller, even though, let's see, 1.5. Yeah, you can kind of see the difference in the variables is the change. So this is an important distinction because we don't always want to have to deal with the fact that we're using this remap, which gives us this really cool geometry, but I'm not okay with my geometry being this, because I'm trying to control cell size, but I want my thickness to remain constant. So I'm going to show kind of a short and dirty without really explaining too much. Again, there's a lot of resources that go into this a little bit more in depth, but I'm going to use this vector field from gradient, and then for my field I'm going to take this remap field prior to offsetting, which we see here. I'm viewing the scalar field. We see here that we're already starting to get this field looking a little bit wonky. So when I thicken it, the thickening is using this kind of remapped field to go from. So I'm going to take this field, I'm going to look at the vector field. One of the things to note is that you can't visualize a vector field. However, if I look at, give myself a variable, this field variable, I can look at this field, their length of the field. So this vector field is using this remap. What's interesting to note again here is that once I remap the field, it kind of, what I don't want is it just extends infinitely. So I will also go ahead and set my field bounding box with this remap field. When you're dealing with normalizing your field to try to make your thicknesses all be the same, I have a couple of blocks that do it kind of automatically, but it always includes the ability to take this bounding box, and that just improves the speed of the algorithm. So let's go ahead and look at this field real quick. So I bounded the field. That also makes your lines look a little bit nicer. Just as a side note. So I'm going to bound the field. I'm going to create this vector field, and then I'm going to go ahead and look at the length of the vector field. So what you'll see here is, number one, your computer will start to go slow. Let's turn that to 100. Let's put it at 0. All right. Here you go. So for the people that kind of know and understand math, the vector field from gradient is essentially looking at the each point in space, and it's looking at the derivative of that point. So the derivative of a curve usually is a kind of line tangent to the curve, which describes the slope at that point. So the vector field itself is looking at the field, and then we're looking at the length of the derivative. And what we're going to do in order to do the normalization is we're going to take this field and divide it by length, divide it by the localized change. And because implicit representation is fields, my field exists everywhere, obviously bounded, and then the length of my derivatives exist at each point, kind of matched to that field. So if I divide one important note, a lot of the times I'll take this length vector field and I'll run it through, again, the smoothen field algorithm. It's yelling at me. Why is it yelling at me? Alright, so even though I have this vector field that's already been bounded, it's still yelling at me, because when I convert to a vector field, it still is extending out into space. So I can do the same thing here. Set my field bounding box. I'm just going to grab the same bounding box. I'm going to take my vector length. What this number is, essentially gives it kind of something to smoothen. I don't want to look at that. Go away. So if you're dealing with beam-based lattices, This should probably be at least half. The grid size should be at least half of what your beam thickness is eventually going to be. That's just the rule of thumb that I use. It's not that necessarily anything official. So, you know, up here my offset value, wherever we're at, offset body, we'll go ahead and make that 0.5. We'll match the grid size to 0.5 since I'm offsetting bidirectionally from the non-dimensional beam, so the offset will be a millimeter total thickness. So I'm going to go ahead and make my grid size match that in particular. Obviously the size of your bounding box and then the grid size in particular are really going to determine how fast the smoothing field is going to run. However, you see here that we kind of have something that doesn't look the prettiest. When we go ahead and do this, we smoothen that field out quite a bit to make it look a little bit nicer. So this is our smoothen. So now what we're going to do is we're going to take this, the length of our derivative, and we're going to divide that by kind of this remapped field. All right. Let's go back to this, make it 0. All right. So one of the things you'll notice immediately is that we're kind of, everything is a little bit nicer and smoothed out. We still have not gotten rid of what's happening, this anomaly, but basically the distance from the beams to every single point has been normalized now. There are a couple different things that you can do after you divide this in order to make sure that your results are sound every single time. This is essentially fills in like values that are not a number with something. So the idea is here, if that we hit some sort of weird fuzziness by doing the division and something is divided by 0, that's going to result as a potential kind of bad data point in the field. So we'll go ahead and throw this in here and say for every bad data point that you get, just go ahead and return 0. This could be a little bit more calculated as well. I've actually kind of messed around with trying to force values to not look the way that they're supposed to, kind of periodically, and then telling this not a number fill to shoot me give me a value whenever it sees not a number, and you can actually do some pretty cool stuff with that. Just for anybody who wants to potentially play with it. So, all right, so I have my divide, my derivative by my field. I've attempted to kind of auto fix anything that's bad. And now I'm going to take this field, and this is my normalized field, and that normalized field is what I'm going to put into my offset body. All right, so this is actually something that looks a lot more like a 1. You can see that my beam lengths have been normalized. Some of the visualization here is going to be dependent on what your resolution is, as well as what you choose for your smoothen field. But immediately you can see that that my values have been normalized where I want them to. Here's something that's interesting. So I turn my distance down to 0.25, and you can still see here that I have a little bit of a different beam length, and that's just because I'm smoothing out my derivative field again a little bit too much. If I want to turn this down, great, my lattice is going to look like I want it to, but just note that smoothing out something that's got a relatively large bounding box is could potentially have some speed related results. We'll go ahead and rate this run. So again, understanding what's happening with your gradient, how your gradient's changing, especially if you're using these remap fields where you're trying to change the implicit body, the surface level body, which gives you potentially unintended results for what your geometry is going to look like in your field in particular. I think that's just my resolution right now, is what's making it look like that. So here you can see that this field in particular, we were able to take over X and remap it to change its cell size volumetrically, while also trying to avoid some of the pitfalls of what happens when you do that and you kind of stretch things out unintentionally. There we go. That looks a lot cleaner. So here you go. So I have this nice, really pretty lattice. You can see in the Y direction, and then up here in the Z direction. We didn't change our cell size. We're just ramping here. And I have a couple examples that I can show, which is no, I don't want it to show that. You know, probably at a later date, you know, which is using kind of this sort of shape remapping idea, which is going to alter your cell size as a function of a lattice's distance from something. Really cool in the medical device field. You know, when you're talking about trying to mimic certain sort of tissue properties or things that we see in nature, we see a lot of shape remapping. You know, essentially a structure's response to a physiological load or external force or condition changes the cellular response to that, which is really cool to see. I'm sure that there's a lot of other applications in heat transfer, fluid flow, things like that, where you could also use that to control kind of a TPMS or gyroid field to direct fluid flow. I think, again, Blake's got some really cool things of how you showing kind of the control over that kind of these multi-periodic fields in space. Yeah, that's about it. You know, the only other thing I wanted to show, which I don't think I showed, was just the field visualization. How you can use. Here, I'll show something a little more scalar. So here's our cube. We're gonna take again and alter here to here. Actually, no. What I want to show is -1 to 0.1 or to +1. Here's to here that this is kind of a more direct result. What we're doing here is taking like a really small, you know, transition from one to the other, which potentially is going to give us some kind of yucky or not very good values there. Again, I like to use the smoothing field to help with this. All right, yeah, a little bit nicer. Not necessarily best, but a little nicer. So, but you can see here that the values are changing kind of directly at the x-axis from one to the other. So I have a really finite control over my gradient here and the spacing here as it steps, and then a very different gradient or larger gradient over here. So a different way to do it, I can change this field to x plus y, which changes the value here, which I think is really cool. Obviously, you know, the field viewer only works, you know, as a single plane. I can go ahead and take a look at how this is changing in space. So you can see at 1, 1, 1, because I'm doing x, y, and z, my gradient here is pretty close to constant. Right there, my spacing is the same, but in any other value, different than normal to this particular field that I've chosen in my gradient. So you can control these gradients three-dimensionally, only visualize them two-dimensionally, which is why a lot of this is fairly simplistic in nature, as far as the visualization aspect. So yeah, I mean, I hope that that this has been informative and that you kind of have gotten a little bit of an example of how you can control these fields in space. I mean, obviously there's a ton of more stuff that you can do with it. You know, we definitely could go a little bit more in depth with how you do that. You know, being mathematically sort of based as far as the manipulation of these particular structures and geometry in space, being able to add bodies together is going to change and essentially combine their fields. It works as similarly to a Boolean union. Subtracting them creates this really cool kind of medial field. And again, nTopology has resources that show this in particular. But if you take a sphere, and I think we had a cube down here somewhere. I'll just make a new one. It's already kind of messy enough. And you take the center point and make it, you know, -5, and make this one 5. give them some distance. The field here, which again, there's some visualization of them in particular, but the field here is really cool in that we have a a positive side and a negative side, and essentially exactly where these fields are intersecting and colliding with this really cool zero plane. So from a surface standpoint, you can use this to pull surfaces in nTopology and use those surfaces to define sort of this distance field of a positive to a negative. And again, what we've shown here that's really cool is understand where your gradient is in space, because I can take this particular gradient and I can multiply it by values, and that gives me a lot of control over where the distance is. So if I have my geometry in space and I see that this cube is 10, on the front side here I have -5, and out here I have -10, I've halved essentially that sign distance field by multiplying it by that value. Similarly, by using the ramps, we can take this field and I want to compress it in a certain direction in y. So I'm going to say, you can see here that I have this larger relationship here, and then I'm going to compress it over on this side as a function of y. So using the combination of ideas that we have here, again, it really gives us some cool control over what our values are, being able to take and manipulate these values, being able to look at these sign distance fields in space, being able to take the fields and smooth them out to give us kind of some additional options, and it really shows you the power of nTopology's control over the invisible, rather than just what we see as visible thing in space. And so obviously if you have any questions, feel free to hit me up. I'd love for you to comment on this video, let me know. I know it's been a lot longer than normal. Thanks for watching if you sat through the whole thing, or even just kind of picked through and looked at stuff that you thought was particularly interesting, and look forward to keeping to kind of pump out the content. So see you guys later.